running, and so the first time it goes through, it'll do the while loop, and it'll just 2 while loops, just throw while loops.
All right, how's everyone doing?
Yeah, pretty good.
How's Thanksgiving food? All right, any questions? Besides how to pork bomb a Raspberry Pi? So we talked about fork. Let's talk about signaling. So this is stuff, I'm not going to hold you responsible for the details of any of this. We're not going to have questions on the exam where you have to write code with forks and execs and stuff like that. High-level concepts maybe, but this is all stuff that you'll see again in a few different venues. But we're just kind of playing for now because it's like Tuesday. So we left with this, right? So this was calling fork 4 times. And it gives us a bunch of output. And some of this output even came after we got the prompt back from bash, right? Because we created processes and they go off on their own life, and somewhere along the way they started calling fork and producing output. So we can create processes like this. So if we want to signal processes, if we want to send information to processes, one way to do that is with the kill call. So kill is both a bash command, right? It's got an entry in chapter 1 of the manual pages, and we can just say kill process ID. But it's also a callable function in chapter 2, so a system level function. We can call kill, and we can give it a process ID and a signal that we want to send to a process, and it will inform the process with that signal. And remember, there's a number of different signals that we can send. So let's play with this. So let's call fork to make a new process. So if the process ID that comes back from fork is a 0, we are the child process. And we'll go to sleep for a while. And then we'll just exit. Otherwise, we're the parent process. And we'll sleep for a while and return. Alright, so it's going to create a pair of processes. We're going to let them both sleep for 2 minutes. Alright, so they're both hanging out there sleeping. And if I do a ps-l, we've got bash, I guess I got a vi hanging out somewhere. We've got 2 versions of this function, this program, Go, right? We've got this first instance of Go, my executable program, whose parent process ID is bash. And then we have the second instance of Go, whose parent process ID is 9941, which is the first instance of Go. So this program created the second program, right? And they're both kind of hanging out there running. And after 2 minutes, they would terminate, but I can just Control C to terminate them, and they both go away. All right, now suppose the parent, instead of sleeping 120 seconds, just exits as soon as it's done creating the child. So So let's run this in the background. There's the parent and the child. And we got a message saying that Go has exited, right? Here's the other version of Go. This is the child process, 9967, but its parent's process ID is now process 1. Why? Because its parent died. Okay, and it became what's termed an orphan. And orphan processes get adopted by process 1, which is called a NIT. Because every process needs to have a parent.
Wait,
So
it's called init?
init,
Like
INIT, like initialize.
Oh, wow.
Right, so process 1, its parent's process ID is 0 because it doesn't have a parent, sbin/init. That's the first process created. So init adopted this orphaned process. And then after a couple of minutes, that will go away. All right, so that's one thing, right? Every process has a parent. If the process's true parent dies, it gets adopted by process 1. All right, we can go in the other direction. We can have the parent kill the child process. And I'm just going to kill this process right now, so 9967. All right. So the parent process, let's kill the child process, right? And we got the child's process ID from the call to fork. And I'm going to kill it with extreme prejudice. So signal 9 is the unstoppable kill signal. It can't be blocked. It will kill the process immediately. There's better ways to kill a process. Normally, if you send a term signal, which I think is 5, it will shut the process down gracefully. But this one just like right in its tracks. So I'm the parent. The child didn't even get a chance to say I'm the child, and they're all gone. Now suppose the parent kills the child process and then goes to sleep for 120 seconds. All right, so there's the parent. Did I compile? All right, so there's the parent, and it's hanging out. Well, now if you look, we've got our bash shell, process 8872, which is the parent of this instance of Go, which is process ID 1015, and that's the parent of this other instance of Go, which is listed as defunct. Okay, a defunct process means it's been killed, but it's still kind of hanging around. It's been killed, but it hasn't like stopped existing. So this is a zombie. And the state column over here, the Z, that means it's a zombie process. And if I run the top command, it'll say I've got one zombie kicking around on the system. So a zombie is a process that you kill, but it hasn't actually died yet. And it's zombied because of the way I killed it. I killed it with this signal 9, which means it didn't have a chance to orderly shut down. And as long as that parent process still exists, there's resources being kept around on behalf of this killed process.
So I see that there's like zombies, you didn't dash elf, and then there's like demons. Is that because people who are into computers are nerds, or
Most likely.
Okay, I didn't know if there was more background on.
So elf is just coincidence as far as I know.
Oh, okay.
It's just an easy one for me to remember. But zombies and daemons, yeah, are probably nerd factors.
Okay, cool.
Because who doesn't want zombies in their system? I mean,
Clerics.
yeah. So that zombie should go away after 2 minutes when the Go process exits. So signaling is one way to send a message to a process. And we can trap those signals, and we can say, when I get this signal, let's do something in particular. Okay, that's done, so the zombie's gone. I'll have to look up traps later. We can set something up that will respond to a signal in a certain way. We'll play around with that next week. But signaling is a pretty kind of sort of heavy-handed way to communicate with another process. So there's more nuanced ways to do this. All right, so we know about the system call, right? To execute a command like that. And we know about forks to create a new process. System is really just a combination of fork with one other command, which is called exec. And exec comes in a lot of varieties. We're going to talk about exec v. And so there's exec L, exec LP, exec LE, exec V, exec VP, and so on and so forth. These all kind of do the same thing, but they have different details in how we use them. But let me give you the basic idea. So exec v expects two arguments. The first argument is a path to presumably an executable program. The second one is basically a car star star, similar to what argv looks like in main. I don't really care what value I pass here, but I need to pass something that the compiler will be happy when it sees. So I'm just going to pass it the argv that main got called with. And the first argument I'm going to use is bin date. Okay, so what am I going to do? I'm going to print out a message in the beginning. Here we go. I'm going to call exec v with bin date and argv, and then I'm going to print out a message afterwards. And if I run that, it says here we go, and it prints out the date. And it doesn't print out that second message. All right, so let's change this. Let's just do a system bin/ps and a few prints. Let me do a ps-l. I can't do a -l. All right, so there's our bash shell. The bash shell created this program E1 that I executed. When I said system, it actually created a new process to execute sh, that's the Bourne shell. And then that shell sh executed the command that I asked to run, which was ps. If I do exec, when I said system, right, This is my bash shell, process 8872. It created a process 10116 to run my program E1, and that created a bourne shell, and that created the command at PS. But then when I said exec v bin PS, here's what my process status looked like. I had my bash shell as usual. I had a single command called PS with the same process ID that E1 used to have. So here's what's going on. You say main, or E1, name of our main program. And that's process ID 10116. Okay, if I call system, it's going to create a new process. That process is going to start executing SH. That process is going to create a new process which executes PS. And we get those 4 lines of output from PS. When I say exec bin PS, what happens is the actual essence of this running process, right? This process has code associated with it. The code came from this file called E1. All of that stuff gets replaced by the code inside this file called /bin/ps. So exec v is a function that will open up this file bin ps, read the binary code out of it, figure out which of that code should go where in memory, and then overwrite its own memory with that stuff. And after the call to exec v is done, E1 is no longer what's running. What's running is now PS. And it has the same process ID that E1 had.
Why would you want to use that?
This is the way processes get created. So we use fork to create a clone of ourselves, but unless we want to run 1,000,000 copies of ourselves, that by itself is not very useful. So to make a new process, first we clone ourselves, and then we have the clone transmogrify itself into some other chunk of code, right? Change its essence so that it's running something from another file instead of the clone code that it got from the parent. So it's really fork followed by a call to exec that we use to create a useful process, and that's basically what the system call does. It forks and then it does an exec. But exec is kind of creepy, right? Because it's like overwriting your DNA, right? You're still sitting in your apartment playing your Xbox, but you're somebody else now, right? You've found someone's DNA and you've loaded it into yourself, and now you look and act and sound and are this other person, but you're still in the same place that you were, doing the same thing that you were. That's kind of what exec does. And it's just the way that processes are handled in Unix. So we do a combination of fork and exec. You had a question? No?
I did.
I thought you did.
I did, but I didn't remember raising my hand. I probably did.
Okay.
So when you create like another process using PI, like the ID, if you wanted 3 processes going on at the same time that were all like different sets of code, would you need to like do one branch so then you have a parent and a child and then another parent and another child? And that would be how you get.
You could do it in a number of ways. So you could have the parent call fork multiple times.
Right.
Right, so you can do something like okay, so call fork, save the return value in C1. So this creates a pair of processes. If C1 is not equal to 0, C2 equals fork. So now you've got a parent with a child whose ID is C1 and another child whose ID is C2. And both of those are owned by the parent. And that's a more controlled way to fork because it's always the parent process that's creating the sub-processes then, as opposed to, potentially having a child create a new child. That's where you're more likely to accidentally fork bomb yourself.
And so let's say that the three processes all have different amounts of code that they're running.
Mhm.
Is there any way to return values to the parent function?
Yeah, we can communicate. Yeah, we're heading there.
Okay.
All right. All right, so the other thing to note here is this last print statement, which says that was fun, never gets executed. Why? Because after the call to exec, this code is no longer what's being run by the process. The code that's being run by the process is all of this stuff, right? The stuff that's in bin PS, there's another elf. Stuff that's being run by bin PS got loaded into memory, and now after the return from exec, right? It's running the first line of bin PS.
So every time that you run fork, will the child process get the same ID, or is it going to be different depending on?
It's different, and it's on this system it's sequential. Some systems it's randomized.
Okay.
But it's whatever. 10.155 was the next one. 10.156, 10.157, and so on. All right, so that's exec, and that's the fundamental way that we create and run new processes. But it's bundled up for us inside. It's called a system. All right, so system uses fork followed by execl to execute a command. And the execl it actually does is it calls bin sh, right? And then says sh-c, and then it puts in the actual command that you put in as the argument to system, so it's running your command under the Bourne shell.
So the system is just the same as execl, but with specific parameters?
Yeah, exactly. It's fork followed by execl. All right, so first it forks to make a child, and then a child does the execl. All right, so we can do a fair amount of stuff with this. But there's a fundamental problem. Right, I can run this and I can execute the date command, right, and see what the date is. But there's no way in here that I can capture the output from that date command. All right, this is just changing this program into bin date. And if I do this with a call to system, right, the output just goes to standard out. And we can write it to a file and read it, but that's kind of a pain. It works in a pinch. But it would be nice to be able to execute a command like we do with system, but somehow read the output of that command and load it into a string and then manipulate it inside C. So another function is popen. So popen is kind of like system. It lets us specify a command that we want to have executed, but it also works like fopen. So remember, if you want to manipulate a file, we can use these function calls. We can say fopen to open a file, and it returns a file pointer to the structure, uppercase file. And we can use the return value from here inside things like fgets, right, instead of standard in. And we can use it inside fprintf instead of standard out. And we can use fclose to close something that we opened with fopen. Okay, so this is for file I/O. So we also have a thing called popen, which returns a file pointer, and there's pclose. And we can use fgets, and we can use fprintf, and all that usual stuff. The difference with popen, though, is that popen actually creates a new process and executes a command, the first argument to popen. So instead of letting us do input to, from, and to a file, it lets us do input and output to and from a process. So let's do file fp equals popen. Let me get rid of these messages here. Let's do popen bin date. And just like fopen, we have to say, are we open for reading or writing? So let's open it for reading. Okay, this is going to do two things. It's going to execute the command bin date in a new process. And it's going to connect standard out of that process to this file star fp. So let's make a character array. Holds 120 characters. Let's do our popen, and then let's just do an fgets. So temp is a character array, 120 is its length, and let's fgets from fp instead of standard in. And then let's print out this character array that we got back. And then let's close fp when we're done, just to be nice. So if I run this, my call to fgets returns the date. So we're running a command, but we're actually capturing its output. And in this case, we're loading the output into a character array, and now we can do whatever we want with that. We can save it, manipulate it, examine it, parse it, and so on and so forth.
So does FP point to standard out, or is it somewhere else?
FP is pointing to a file descriptor that's been connected to standard out of the bin date.
So if you kept putting stuff in standard out, would it also show up in that?
Yeah, so let's do a popen on /bin/ls. And let's do fgets in a loop. So while fgets is not equal to null, let's just print out what we got by calling fgets. And so each time we read from fp, we get the next line of output from bin/ls. So now we've got access to file information in our current directory. And this is still being run through a shell. So we could say something like ls*.c, and it gives us information from ls just on the .c files. So now we could write a C program that looks in the directory and tells us all the files that are in that directory. So this is one of these pieces of machinery, right? Like the first time you discover a box cutter, right? It opens up a whole world of possibilities, and there's things that you may not, box cutters may not be intended to use, but since you've got this in your toolkit, you can use it, right? For taking the insulation off the end of a wire, because you don't have a pair of wire strippers, right? So this is one of these tools that it's a simple thing, right? It's one function, it's a popen, but it lets us execute any command we want and capture its output. And once you can do that, you can start building on top of that by using C programming, right? This is why we learn how to program, because if we want to make something that traverses your entire directory tree, right, what could we do? We could do a popen on /bin/ls dash L. Right? Well, let me do this on something more interesting. Let's do a bin slash ls dash L on my home directory. Right? So that's showing me a list of everything that's in my home directory. Well, when we do an ls-l, this first character here is coded. If it's a D, this is a directory. If it's an L, it's what's called a symbolic link. If it's a hyphen, it's a plain file. If it's a B, it's a binary type device. If it's a C, it's a character type device, and so on. So if I wanted to get a list of directories, what can I do? I could say if temp bracket 0 equals D, then let's print out what that is. Let's just print this out just as a %s. Alright, I got a list of directories in my home directory. So those are all my subdirectories. And I can put this in a function, and for each of these files I can pass that to my function, which will do an ls-l on that, and look for things that start with a D, and they'll tell me subdirectories below that level. And so I could write a C program that I could give it a starting directory, and it would show me every single file in the directory tree starting from that point. Right? And this is what the find command does. If I say find slash, that'll start at the root directory, and it'll find every file that sits underneath that directory. So this will show me every file on the system. It'll never finish. Alright, but that's just a C program. Now there's other ways to do this, but you know, this is what I mean. If you have one tool, you can do a lot with it by building on top of it. And the way we build on top of these things is by writing C code.
So this would still only work on a Unix system, correct?
Yeah, so if you're on a non-Unix system, I'm not sure what happens if you try to do things like fork or exec or even system. Not sure. But it'll work on a Raspberry Pi, because that's Unix. It will probably work to some degree on a Mac.
Do you think, are there similar ways to achieve these things on different systems?
Yeah, so pretty much every operating system is going to have some way of creating processes, but it might be very different from one system to another. I don't know how it goes on Windows or on DOS. I haven't played around with that.
Are these things pretty straightforward for all programming languages to have?
Yes and no.
Okay.
I don't think there's a universal for all languages. So in Java, we do something very different when we want to create processes. Okay. It's actually built into the language itself.
Whoa. In
some sense. I mean, there's objects, classes like thread that we can use. This is really, it's very much to do with Unix more than C. Right?
Oh,
C lets us call functions, but the functions we're calling are low-level system functions. Whereas Java, we actually have classes for creating a new process and communicating between processes and things like that. And we'll play around with those in Spring for sure. All right, so p-opens, we can use a p-open, and we can read the output of it. We can also do a p-open. So let's pick on the BC program, and let's say let's write. And let's write 2 plus 2 into BC, and then close our file pointer. And remember, BC is just this calculator program, so if I say, some arithmetic expression, it evaluates it for me. So So let's open BC with a P open. We'll open it with a :W to say we're writing into this process. So what we print to FP will feed standard in of that process, which means it will be input to the BC command. And so we're going to write 2 + 2 followed by a new line. And so if we run E1, it gives us a 4. 2 + 2.
Does this work on directories that we do not have access to?
If you have execute permission on a directory, then you can search it.
Okay.
So if you're on the Linux server and you go to somebody else's home directory and you try to do an ls, you'll get a permission denied. But if you go to /, for example, everybody has execute permission on that, so everybody can search / and see what's listed under there. So just as a point of note, let's go ahead and send 2 + 2 new line to the BC command, and let's sleep for 10 seconds. And if we do this, it's already sent 2 + 2 new line, but we didn't get our output from BC. It didn't say 4. And we won't see any output until 10 seconds later, after we call fclose, and then we actually see the result. So the problem here, or the feature, depending on how you look at it, is buffered output. Okay, so we've bumped into this a few different times now. When you say fprintf, when you send something to a stream, it doesn't always get sent right away. When you say fprint 2 + 2, this string 2 + 2 new line goes into a buffer, a holding area, but it doesn't get sent to the BC command right away. It will get sent after I say fclose, or it will get sent if I say fflush. Right, that'll force it to go out immediately. And now, as soon as that fprint and fflush execute, BC gets the 2 + 2, and it'll respond, even though we haven't closed the FP yet. Buffered I/O is one of those things you just got to kind of keep in mind, because sometimes it'll catch you, and you can waste, a whole night trying to figure out why your thing isn't getting written. And in fact, it is getting written, it's just not getting flushed out, because you didn't flush it, and you didn't close it. So here's another example of that. So p1.c, so I'm opening this file called we're just using fopen here, okay, nothing to do with popen. Just opening a file for write, and 10,000 times we're writing out, this is an important message. And I'm going to sleep afterwards. And I'm going to call close. All right, so if I kill this right now, and I look at my file, it tells me incomplete last line, and it only wrote 9,910 messages, and then part of that next message. Well, I wrote 9911, and then part of the 9912th message. You got the THI out. Right? And I clearly said 10,000 times, let's write this message out. And that's in a for loop, and that definitely finished executing. Right? We can print a message here. Right, so it's all done, but that file's not completely written. Right, why? Because when you do an fprintf into a file, it doesn't directly go to the actual hard drive. it goes into a holding area. Now, if I do a call to flush, right, if I do an flush on FP, and I control C it, my file's perfectly fine. So flush says take everything that's been queued up to be written to the file, go ahead and actually write it out. And if I actually go ahead and close the file, that has the same effect as calling flush. It forces everything to be written out. This is what happens when you put a flash drive in your computer. You write a bunch of stuff to it and then you just pull the flash drive out. Right? Unless your system is set up to handle that, what can happen is when you copied stuff over, it executed a bunch of printfs, right, effectively, to write things to the file on the flash drive, but they didn't actually all get written out. Some of them are still in this sort of holding tank waiting to be written out. Now if you say eject, what that will do is it will go through all these buffers where things are held to be written, and it'll say flush those out. And then when you eject the drive, right, now you can remove it and all the files are intact.
So why did you choose to flush it after the for loop and not inside of it, like after every print statement?
So you could do it after every print statement, and when you set up your system for fast removal, that's basically what's happening, is every time that you write something to your flash drive, it gets forced out. Right? It degrades performance, but it means you can pull the drive at any time and it works fine. When you set it up for, I forget what the other term is, but you know, where you have to eject it, basically it never forces that flush until you say eject. The problem with doing a flush every time is if you're writing to a hard drive, right, and your hard drive is spinning 5,000 times a second, how do you write to a hard drive? Well, you've got a disk, right, so it's a physical platter and it's spinning typically 5200 RPM or 54. And your file begins right here. Well, you have a read-write head sitting over here, and you can't write to this part of the disk until that part of the disk is underneath the read-write head, so you have to wait for typically half a revolution, right? So a 5,000th of a second, that's a long time. If your machine can do 3 billion things a second and you have to wait for a 5,000th of a second before this comes under the read-write disk, that's a huge delay, right? And every time that I go through my for loop, if I do an flush, potentially I have to wait that long. Now it's not that bad because there's other levels of caching at play also. But that's the basic idea, is doing actual writing to a file or to a command or to a network connection is slow compared to CPU speed. So things get buffered for efficiency, and then once that buffer is full, it goes, whoom, flushes everything out. Because once this has spun around, and this part where your file begins is under the read-write head, if you want to start writing, you know, 1,000,000 bytes after that, that's pretty efficient, right? Because they're stored in a way that as the disk is spinning, you just keep writing. But it's the seek time that kills your performance. So there's all kinds of real-world concessions when we do file I/O and network communication and so on. So buffered writing will be a topic in 223. And in C, we can do buffered I/O by doing things like printf and fgets. We can also do low-level I/O by doing things like read and write. And these are Chapter 2 system-level commands. And we'll play around with these a little bit next week. Assuming we have time next week, we'll still talk about how to communicate between processes using something called a pipe. And it's the same kind of pipe we use with a vertical bar. But we can create pipes from C programs, and we can read and write different ends of those pipes using read and write calls. All right, so that's it for this week. Monday we will begin presentations on PA5. So someone from your group should have a laptop that runs your code. Bring that in. We have an HDMI cable, we have a VGA cable. If you have anything else, you may need an adapter. Worst case, you can kind of hold your laptop under the camera and get away with that. So we'll go through presentations starting on Monday, and then when we're done with those, we'll come back and wrap up a few more things on processes and review for the final, and that's it. All right, so have a great break. I will see you next week.